Okay, so we are in chapter 3 now, and chapter 3 starts to shift the focus a little bit. So chapters 1 and 2 started with an emphasis on linear systems, and then from there launched into a lot of work on matrices. Chapter 2, determinants, that's an operation that we perform on square matrices, so the focus is still on matrices throughout that section. Chapter 3 is going to take a more geometric approach. I guess you could say that chapters 1 and 2 were a bit more algebraic in their nature. Chapter 3 is more geometric. We're going to be talking about vectors in 2 space and 3 space, and then a generalization of that, which is n space. And there's a visual representation for those, so it feels much more geometric. We're not going to see quite as much with matrices at first, but then we're going to start working the concept of matrices into this vector concept. And what I'm planning on doing is making a video at the end of chapter 3 that establishes several connections between the work that we did in the first 2 chapters and this more geometric work that we're doing in chapter 3. So let's go ahead and move on, starting with a lot of terminology. And I'll mention this as well before I get into this. Chapter 3 is going to feel like almost all review for you if you've had Calculus 3. But still pay close attention. There's some notational differences in the things that we do here compared to what you would be doing in chapter 3. In Calculus 3. And there's also going to be some things that you would not have necessarily covered in Calculus 3. So make sure you still watch the whole videos, even if the whole video series, even if this is, review for you. Okay, so for our purposes right now, a vector is an object that possesses 2 measurable quantities, magnitude and direction. In chapter 4, we're going to generalize what we mean by the term vector. We'll define it differently there, but for now, this is what we're going to think of as a vector. Generally, we represent vectors of this type with an arrow, and the arrow has a direction which we determine based on the end points of that arrow. One of the points is called an initial point, the other is called the terminal point, and we'll see some examples down here in a minute. By depicting a vector with an arrow, the direction that it's pointing is what gives us this quantity of direction here, and the length of the arrow is what we interpret as its magnitude. So we have a visual depiction of both of these quantities. Now, if we're talking about a vector in 2-dimensional space, which I have some examples of down here, then we can also think of the direction of the vector as the angle that it creates with the positive x-axis. We won't be using that much, but that's a common thing to do, to kind of give a standard way of measuring that direction. A really important property of vectors in the plane or in space or in any generalization of that is that if a vector has a specific direction and magnitude, we consider that vector to be equal to any other vector in the plane having the same direction and magnitude. So what that means, you can see down here, if I had these 2 vectors, but they are parallel, meaning that they have the same direction, and they actually, let me take that back. Parallel can mean the same or opposite direction. So I should just say that they have the same direction and the same magnitude. Even though this one appears up here and this one appears down here, we would consider these 2 vectors equal to each other. They are not considered to be different. All right. In addition to the terms we've talked about so far, we have what's called the 0 vector. And the 0 vector is the only vector that has no direction associated with it. The reason for that is because the 0 vector is the unique vector that has a magnitude of 0, meaning we would think of it as an arrow with 0 length. But really, that would just be a point in space. So we think of a point in space as the 0 vector, and you can't take a point and orient it in any particular direction. Okay? Now, if you have a vector in space, or 2 or 3-dimensional space, and you have its initial point given as a point in that space, and its terminal point, let's call those P and Q, initial and terminal. We sometimes use this notation for vectors, PQ, with a little arrow over the top, and the arrow should be pointing in the direction of that terminal point Q. Other times we don't necessarily need to know anything about the initial or terminal point of a vector. And in cases like that, which is a little bit more common in our class, we will represent vectors by lowercase bold letters or lowercase letters with that arrow over the top. Usually the arrow over the top will show up if we're writing vectors, not necessarily typing them like I did here, just because I can't bold anything with my pen very well. All right, so now let's take a look at these vectors right here. These are vectors in what we call two space or Euclidean two space. Well, let's take another look at that term in a moment. These vectors live in like the two-dimensional plane, basically. If we impose a coordinate system on the two-dimensional plane, then we could talk about points in this two-dimensional space, and we can specifically single out initial and terminal points for any given vector. Oftentimes, we want to represent vectors in terms of what are called components. And a component is a measure of the horizontal and vertical displacement as you move from the initial point to the terminal point of a vector. So as an example here, let's look at this one right here, actually. This vector has an initial point at the origin, 0, 0, and a terminal point at the point 4, 1. So horizontally, from the initial to the terminal point, I move 4 units, and then vertically, I move up 1 unit. So 4 units to the right, 1 unit up. 4 and 1 would then be considered the components of that vector. And it's a way for us to assign quantities to vectors that make them identifiable. If you have the initial and terminal points of a vector, it's easy enough to see that we can compute the components by just taking the difference of their x's and their y's. So for example, if P is the point x1, y1, Q is the point x2, y2, and we're talking about the vector PQ, then the vector PQ can be written in this notation, AB, where A is the difference between the terminal x value and the initial x value. B is the difference between the terminal y value and the initial y value. Now here's where, if you've had Calculus 3, the notation is going to look a little bit different. In Calculus 3, or other classes where you may have learned about vectors, you have likely seen vectors in component form, but instead of using parentheses, you've probably seen them with angle brackets. In fact, this picture, which I took out of a different book, uses angle brackets for this vector, for putting it in component form. We're actually not going to use that notation in this course. And the reason for that is because in Chapter 6, we're going to introduce something called inner products, which will use that angle bracket notation. So to avoid confusion between a vector and an inner product of vectors, we don't use the angle brackets here. Okay, so you want to get used to writing these types of vectors with parentheses if you're not used to that. All right. Now, like we said before, any two vectors that have the same magnitude and same direction, so in other words, they would have the same components, we consider those to be equal even if they are in different positions in the plane. But for a number of reasons, it's oftentimes useful to take a vector and position its initial point at the origin. We're going to do that a lot when working with these types of vectors. So if a vector has been put in that position, we say that it's a position vector, or sometimes we'll say that the vector is in standard position. So that just means the initial point is at the origin. And even though, again, we're looking at vectors in two-dimensional space here, all of these terms carry over to the case of three-dimensional vectors as well. Okay, so here's an example to help work with some of these terms. We want to find the component form of a vector that has the initial point 1, 3 and the terminal point negative 3, 5. And then we want to graph the vector with those initial and terminal points, as well as graphing the vector in standard position. So let's give this vector a name. I'm going to call it V. And in component form, the x-coordinate should be the difference between the terminal point's x-coordinate and the initial point's x-coordinate. Negative 3, I don't want a comma there, negative 3 minus 1. The second component should be 5 minus 3. It's important that you always do terminal minus initial, or else your vector is going to be pointing the wrong direction. So doing the subtraction, we get this vector, -4, 2. That's the component form for that vector. Okay, next up we want to graph this vector in two places, in standard position as well as where our initial and terminal point are. So I need an initial point at 1, 3. It's 1, 1, 2, 3, right there. So there's my initial point. And then I need my terminal point at -3, 5. So 1, 2, 3. There's -3. +5 would be up here. 4, 5, like that. Okay, so that's my terminal, which means the arrow should be pointing that direction. Doesn't need to be perfect, but having some labels in there helps. Next thing I want to do is take this exact same vector, but put it in standard position, which means this initial point needs to be moved to the origin. Now, one nice thing about having a vector in standard position or as a position vector is that if you know the component form for that vector, that component form is going to tell you exactly where to find the terminal point as well, which means if my initial point is at the origin 0, 0, then my initial point, or my terminal point, should be at -4, 2. Like this. Okay? Now this is a rough drawing, so the vectors are not going to look perfect, but if I had done this with the assistance of a computer or something, you would see that both of these vectors look identical as far as their direction and magnitude are concerned, and regardless of the different position, we consider them to be equal to each other. They are considered to be the same vector. Okay? All right. So I've used some of these terms already, but now we're going to actually define them. So the vectors that we just talked about and sketched were vectors in two-dimensional space. Now, if you take the set of all vectors in two-dimensional space, we refer to that as Euclidean two-space. Although for our purposes, we're usually just going to say two-space. Two implying the dimension of that space, two-dimensional. If you're talking about a vector in three-dimensional space, then that's going to have three components instead of two. In three-dimensional space, we use an x, y, and z axis. So the components of a three-dimensional vector are going to represent the displacement as you move from your initial to your terminal point in the x, y, and z directions. You need three components for that. The set of all vectors in three-dimensional space is what we call Euclidean three space. Okay, and we the operation of finding the components of a three-dimensional vector from the initial and terminal points work the exact same way as how we did it in two space. So here's an example. Sorry, I did want to mention this. The 0 vector in two space looks like, in component form, 0, 0, because as you move from your initial to your terminal point, you're actually not moving at all, since a 0 vector is just a point. So you move 0 in the x direction, 0 in the y direction. Similar, this is 0 vector in 3 space. Okay, so we have a couple of points. This time they're in 3 space, and we want to find the component forms of the vectors PQ as well as QP. So starting with PQ, same idea. We do terminal minus initial, so 2 minus 1, and then 0 minus 5, and then 4 minus -2, which would be 1, -5, 6. Okay? QP is reversing which point is the initial point and which one is the terminal point. So my subtraction will occur in the opposite order. 1 minus 2, 5 minus 0, -2 minus 4. And what I get from this is a vector whose components are the opposite of the components in my previous example. 1, -5, 6, -1, 5, -6. And this is it's easy to see why this is the case, because that's what happens when you reverse the order of subtraction. You get the opposite of what you would have gotten doing it in the other order. This is a way that we can quickly verify if two vectors are in opposite directions but have the same magnitude. Their components will just be opposites of each other. Okay, so up until this point, we've only done a little bit with vectors, but now I want to work towards performing operations on vectors. And primarily we're going to look at these from a geometric standpoint at first. So if I have two vectors, remember the bold lowercase is how we notate those, v and w, how can we think about adding two vectors together? We want to be able to do operations on these the same way we do with real numbers. So a sum of vectors for us we define using something called the parallelogram law. And the way this works, here's an example. Let's suppose we have two vectors v and w, and I want to add v plus w. We use something called tip to tail, which means if I put the vector v in space here, or in the plane, wherever it's supposed to live, then the next vector, w, the one I'm adding to it, I'm going to make its initial point coincide with the terminal point of v. So v takes me from here to here, w takes me from here to here. The sum of v plus w is going to be the vector that has the initial point, the same initial point as v, and the same terminal point as w. Now, what you can think of this as, well, there's a few different ways to think of this. Oftentimes, when you're first learning about vectors, it's in the context of forces. So you can think of this as the result of combining a force in this direction with this magnitude with a force in this direction and this magnitude. You can think of your initial point as a starting place, your terminal point as an ending place, and if I stack these two vectors and travel in the direction of this vector and then travel in the direction of this vector, what I've done is I've essentially traveled from here to here, giving me this vector. There's lots of useful interpretations of that. This last image here illustrates that the sum of two vectors, or adding two vectors, is a commutative operation. Because if I were to add v plus w, it would look like this. But if I were to add w plus v, remember you can move vectors around and they're still the same vector. Their position doesn't matter. So if I move w down here, and if I move v over here, then w plus v still gives me the same vector. And this is where we get this name parallelogram law. When I stack the vectors this way, it creates a parallelogram. That's really important, okay? The fact that that's a parallelogram. We'll look more at that. In fact, we're going to relate that to the determinant much later, the determinant of a matrix. But anyways, that's how we add vectors. Now, that's just using the geometric concept. But if we want to get a component form for the sum of two vectors using the components of the two vectors we're adding, then we need to look a little bit more closely at what's going on there. So here's a couple of vectors that I'm adding, a and b. Okay, and I'm going to say a has components a1, a2, and b has components b1, b2. If you look at A, the components of A, remember, represent the horizontal and vertical displacement as you move from the initial to the terminal point. B, its B1 and B2 represent the same thing, horizontal and vertical displacement. And then if this is the sum of A plus B, as I go from this initial point to this terminal point, notice as I move in the x direction, I'm going A1 units followed by B1 units. So the horizontal component of this sum should be A1 plus B1. Similarly, the vertical displacement, as I go from my initial to my terminal point here, is A2 plus B2. So that makes it very easy to add vectors that are in component form. We simply add their horizontal components and we add their vertical components. That gives us the component form for their sum. All right. We'll do some examples a little bit later, but right now we're going to continue developing different operations that we can perform on vectors. The next thing we want to do is define scalar products or scalar multiplications. In this scalar multiplication, in the same way that you can multiply a matrix by a scalar, we can also multiply vectors by a scalar. So let's suppose we have some positive scalar to begin with, k, and some vector v. Then we define the scalar product of v by k to be the vector that we notate kv like this, and it's going to be the vector that has the same direction as v. So multiplying by a scalar does not change the direction of a vector. However, the magnitude of this vector can change. The magnitude of the vector will be equal to k times the magnitude of v. So here's some examples down here to illustrate this. Just start by looking at these three right here. If this is v, then if I multiply v by the scalar 1/2, I get a new vector that's in the same direction as v, but is now half the length of v. Or if I multiply v by 2, that will double the length of that vector v while maintaining the same direction. Now, that's what happens if we have a positive scalar. But if I were to multiply k by a negative scalar, so if k is less than 0, then kv will be the vector that has the opposite direction and is scaled by the absolute value of that scalar. So, in fact, that's why we call these scalars, because their primary purpose is to scale vectors. So if I multiply v by -1, the absolute value of -1 is +1, which means the magnitude of this vector is going to be the same as the magnitude of v, but the difference is that it's reversed its direction. It's basically traded its initial and terminal point. If I multiply v by a -3, the negative in that scalar will reverse the direction, and the 3 will triple its length. Okay? So we've covered positive scalar multiplication, multiplication by a positive scalar, multiplication by a negative scalar. What if you multiply a vector by the scalar 0? Well, we define that to simply be the 0 vector. Okay. Now, just like we did with addition, we want to take a look at what scalar multiplication would do if we're looking specifically at the components of a vector. So again, here's a vector A, and its components are going to be A1, A2. Now, if I were to multiply A by, let's assume for now that it's a positive scalar C, then we know that this gives us a vector that has the same direction as A, but scaled by a factor of C. So if C is greater than 1, it's going to make this vector longer than this, for example. Because the direction didn't change, and because horizontal and vertical components are still going to be horizontal and vertical over here as well, these two triangles are similar right triangles. The direction of everything has remained the same, which means these angles in here are all going to remain the same. And so that means that these two, the sides of all the sides of these two triangles should be proportional. Meaning, if I multiply this by C to get the new length here, then I'd have to do the same to these components. This will be C times A1, C times A2. So the components of CA are given by these, but that's the same thing as taking a vector, multiplying its components by whatever scalar is appearing out here. And it turns out that's going to be the same thing whether k is positive, negative, or 0. We can simply multiply the components by that scalar. Okay. I'm running out of time in this video, so we'll keep moving on the next one.